we now come to the formal definition of stochastic processes. As input, we need a background probability space, a state space where the stochastic processes will live, and an ordered set representing time with a first time minimal element. Now, usually for us, the time set is going to be either the natural numbers for a discrete stochastic process, or the positive half-line, or possibly an interval a up to b. Given those as input, a stochastic process is simply a collection of random variables from the probability space to the state space, indexed by the time set t. So random variable here, of course, means a measurable map from this measurable space to that measurable space. Now, that is too broad a definition to say anything meaningful about, so we will be developing all sorts of particular kinds of stochastic processes as we go. The minimal information that we'd like to get about our stochastic process is its finite-dimensional distributions. And what that means is we'd like to know, for each finite subset of the time set, what is the joint law of the points in the stochastic process indexed by that finite set of times. So that is, for each finite set lambda subset of the time set, we want this probability measure on s to the lambda equipped with b to the lambda, the probability law of this random vector, if you will. Now, to be clear, this is usually inadequate to characterize the whole process xt. If the time set is countable, it will suffice. If the time set is uncountable, like the real line or an interval, we will need extra information, like some kind of strong continuity properties for the process as a random function of t, in order to use this information to say more complete things about the full process. But in any case, it's a starting point. And so in the examples that we'll consider in this lecture and the next, we'll be primarily concerned with these finite-dimensional distributions. In some sense, we've spent most of the last 3 months studying one particular kind of discrete time stochastic process. That is, an IID sequence of random variables is a stochastic process. It's one whose finite-dimensional distributions are very easy to describe. That is, this law is just a product law, the product lambda times of the law of any one of the variables. Done. We've also spent a lot of time studying an associated stochastic process to that one, that is, the sequence of partial sums. Now notice that I've consciously changed notation here. The summands I'm now calling ck, and the sums I'm calling xn instead of sn. The reason for that is that we want to think of these as the basic objects in a lot of cases and not derived from something else. It's also pretty straightforward to describe the finite-dimensional distributions of these sum processes. Let's look at an example. Suppose that I want to find the finite-dimensional distribution of x1, x3, and x4. By convention, I'll always write them in increasing order. Well, I can write x1, x3, and x4 as a nice function of the increments x1, x3 minus x1, and x4 minus x3. That function f that I'm using here is the function of 3 variables, which is just x, x plus y, and x plus y plus z. If I apply that function to these, taking sums progressively, I will get back to here. So that means that if I can understand the joint distribution of these, then I can understand the joint distribution of these just by pushing forward that distribution by that function. But of course, from our construction here, we can rewrite what those increments are. x1 is just c1. x3 minus x1 is c2 plus c3. And x4 minus x3 is c4. And the reason that it was useful to do this is that because the ck are all IID from the grouping lemma, these 3 random variables are independent from each other. And we can, of course, describe their laws. xc1 and xc4 have the same basic law that we started with, the law of, say, xc1, and xc2 plus xc3 are two independent random variables with that same law, so its law is the convolution of that law. So if ck has law mu, then the law of this random vector here that we're applying f to is mu times mu star mu times mu. And we can apply similar reasoning, writing a vector in terms of its increments like this, in order to recover the joint distribution of any finite collection of x's in this process, so we fully understand its finite-dimensional distributions. Now we see that it made sense to write these vectors in increasing order of indices, at least in this example, in order to use this trick. But relating to what we discussed in the previous lecture, it is often important to understand the progressive measurability of sequences of random variables like this as you keep adding more in. That is, we often need to consider the sigma field generated by the first n random variables. So let's formalize and generalize that a little bit. In the context of a probability space, so we have a fixed sigma field already, if we have a collection of sub-sigma fields, ft, indexed by the time parameter t, it's called a filtration if it is an increasing collection of sets. That is, if fs is contained in ft whenever s is less than or equal to t. Now, heuristically, when we're modeling dynamics, like stochastic processes are good for doing, ft, a filtration here, is supposed to represent the information we have about the system at time t. And so it makes sense that it should be an increasing family of sigma fields, because we, the observer, are not going to forget the information we learned at time s. It's going to stay with us until time t and beyond. Now, the example that motivated this is just if we have a sequence of random variables, which we now think of as a stochastic process, then Fn, being the sigma field generated by x1 through xn, is a filtration. This is typically how a filtration will occur for a stochastic process, but it may be the case sometimes that we'll want to equip a probability space with a filtration from the get-go. In that case, we call it a filtered probability space. That is, instead of just the triple, we have a quadruple. A measurable space, a base sigma field, a filtration of sub-sigma fields of that base sigma field, so that base sigma field is larger than all of these, and a probability measure on f, which therefore descends to a probability measure on each of these sub-sigma fields. Now, if we do it that way, where we have a filtration that we introduce from the start, then the stochastic processes that we'll want to work with had better be well adapted to the filtration. And so we use that term, adapted. A stochastic process is adapted to a filtration if for each t, xt is ft measurable. So for example, up here, this sigma field was designed so that the process xn is adapted to this filtration. Now, we might have been inclined to say, well, why don't we just let ft be the sigma field generated by xt? Then xt is, of course, measurable with respect to ft. The problem is that this is typically not a filtration. There's no reason to think that the sigma field generated by just xs alone will be contained in the sigma field generated by xt alone. But what we can do instead is something like this. We can define ft to be the sigma field generated by the set of all random variables xs with s less than or equal to t. This is such an example when the time space is discrete. Now, in fact, the usual way that filtrations will come about is we'll have a stochastic process and we'll use this filtration so that the stochastic process is automatically adapted. But there will be cases where we want to deal with more than one stochastic process at a time. So we'll want them all to be adapted to the same filtration. And thus we'll need to have a background filtration from the start and make sure that our processes are adapted to it. Now with this language, let's take a look at our sequence of partial sums of IID variables, stochastic process again. That is, we have IID variables ck in Rd, and we let xn be the sum of the first n, and we take as the filtration the minimal filtration with respect to which the process xn is adapted. One thing to note here is that xn is a function of xc1 through xcn for each n, and that means that fn is also the sigma field generated by xc1 through xcn in this example. Now let's think about the random dynamics calculation we did in the last lecture. There we discovered this memoryless property, the Markov property, for those random dynamical systems. And it was described in terms of these projections, conditional expectations. If I have some bounded measurable function of xn, and I condition that on the sigma field at an earlier time. Now before we wrote this as this explicitly, but let's think about it now just as a background filtration. We wanted this to be nicely related to the process, and let's see what happens in this example. If k is less than n, well then let's remember that xn is the partial sum here, so we can write xn as the sum of the first k terms plus the sum from k plus 1 up to n. Sum of the first k terms is just xk, so g of xn is just g of xk plus ck plus 1 plus up to xn. Now this first term here, xk, is measurable with respect to fk. As for the second term, this is independent from fk by the grouping lemma. So this is a conditional expectation of the form g at x plus y, where x is measurable with respect to this sigma field and y is independent from it. And on your homework, you showed that in that case, this can be computed explicitly by taking just the scalar expectation of g of variable x plus these random variables, and then taking that function of a real vector x and evaluating it at that real vector x being the random vector xk. Now that is a function of xk. So it is measurable with respect to not just this filtration sigma field, but with respect to the sigma field generated by just xk. And following exactly the same reasoning that we just did, this can alternatively be written as the conditional expectation of g of xk plus ck plus 1 plus cn given just xk. But this is where we started. That's xn. And so this is the conditional expectation of g of xn given xk alone. And so we see that this process xn has the Markov property. Conditioned on the whole past up to some time k before the present, we get the same answer if we just condition on the instant at time k of the present value. This process is memoryless. Now that shouldn't surprise us, considering that we move through this process just by adding independent things at each step. And in fact, this is the canonical process that fits the mold of that random dynamical system approach that we defined. Here, this process xn is defined iteratively by xn plus 1 is a function of xn with random input noise xn plus 1, where in this case, the function f is just the function f at xy equals x plus y. And we are starting at 0, which is independent of the IID sequence xn. So we knew we were going to get the Markov property here since this process fits the bill. But it's good to do the calculation explicitly to see how it works in this case anyway. Now this might seem like a very contrived, silly example, but it's not. It's actually one of the most important examples of a discrete time stochastic process. These processes are what's called random walks. To be more precise, let's consider the special case where we're taking values in Rd, and the common law of the IID entries, C, have this form here. They're discrete random variables that can only take in Rd 2D different possible values. And those 2D different possible values are plus or minus the standard basis vectors. So for example, on R1, we're talking about a Rademacher random variable. In R2, we're talking about a random variable that can either go left or right or up or down, each with equal probability. These partial sum stochastic processes in these cases are called simple random walk, or symmetric simple random walk, to be clear. And graphically, you can imagine what they're doing. They start at 0, and then at each time step, they move in one of the coordinate directions, or it's negative. And at the next time step, it chooses randomly to go left or right or up or down. Then maybe it goes back and up again, and you see how this works. And so on. There are a plethora of questions that you can ask about the long-term and medium-term behavior of this stochastic process. We have a complete understanding of the finite-dimensional distributions here, as we saw on the last slide, but we'd like to answer questions like this. Will this process ever return to its starting point? And if so, with what probability? How often does it return to the starting point? Does it return infinitely often, almost surely, or with some non-zero probability, or does it almost never return to the origin? How far does it get from the origin in time t on average? How long does it take to get that far away? How long does it take to get over into this set over here, and so forth? There are many, many questions that we could ask. Now, we could undertake, for, say, the rest of this quarter, a detailed study of this precise stochastic process here in ZD, and fully answer all of these questions using some nice harmonic analysis methods that were invented in the 19th century. We're not going to do that right now. We're going to fit this into a larger picture of stochastic processes and develop tools that will work to answer these questions in greater generality. And in order to head in that direction, I want to consider another kind of basic model of stochastic process first, instead of being in discrete time, in continuous time. Although we're going to build it from a discrete time stochastic process. So here is another example. Suppose that we have a non-decreasing sequence of random variables. Now, the one we just developed is definitely not non-decreasing, because even in the case of R1, it can go back and forth. But we could construct a similar one, not with those particular random variables that we had there, the Rademachers. Suppose that the xn's are constructed just like we did before, as the partial sums of some random variables ck, but this time we'll arrange for those ck's to be random variables that take value in the non-negative reals. Then xn will be a non-decreasing sequence. Such a non-decreasing sequence of random variables is called an arrival process, where we think of the xn's as talking about the arrivals of some events. For such a process, there is an associated counting process, defined like this. For each t, nt is the sum over all n of 0 or 1, depending whether xn is in the interval from 0 up to t. Now that's a convoluted way to write that this is the supremum of all n's, such that xn is less than or equal to t, because I'm just adding up ones constantly until xn gets past t, since the xn is non-decreasing. This is called the counting process associated to the arrival process xn. And if I draw the graph of nt, it looks like this. It looks kind of like a cumulative distribution function, except these jumps are always height 1. In principle, they could be height higher than 1 because the process could jump twice at the same time, depending on what these ck look like. Those CKs have a name, by the way. We can just write them instead of like this. We could start with any non-decreasing process and define CK to be xn minus 1. Those are called the inter-arrival times. And for an arrival process, these are, of course, non-negative. Now, if those inter-arrival times are actually IID random variables, we call the arrival process a renewal process. A lot of words being thrown at you here, but it's all to get to one particular renewal process, the Poisson process, which is the fundamental example that demonstrates all of the tools that we can work with for stochastic processes in a fairly simple and understandable package. And we're going to devote the next lecture to its study.